Okay, let's talk about solution concentrations. So solution concentration, we can talk about a couple ways. We can talk about it kind of generically. So in terms of a solution being dilute or concentrated, and so that tells us just the relative amount of solute per solution. Okay, and so if we classify a solution as dilute, it's just telling you that there is a small amount of solute in that solution. Whereas if we classify one as concentrated, that's telling you that there's a large amount of solute in that solution. Okay, but most often we actually want to know the concentration, so how much exactly is in there. And so for that, we usually give that as a ratio, or it's calculated from a ratio, but it's reported then by dividing those two values. And it's basically giving you a measure of how much solute is dissolved in a solution. It could be a ratio of the solute over the solution, so over the total, so how much of that thing that's being dissolved is in the total solution, or it could be the amount of that thing being dissolved is in the solvent, okay? So it can be either way. Most common, the bottom number in that ratio that you calculate is the solution, so the total. And there's actually multiple units of solution concentration. Okay, so it depends on the application. People will use different units for concentration, meaning they actually use different units for their solute and their solution, or their solute and their solvent. And so then when you divide those things, they come out in some different overall unit. And so we're going to talk about some common concentration units, and then we'll do some examples calculating concentrations of solutions in these different concentration units. So here's a table that gives you some common concentration units. So we have some that are percents, so a percent by mass or percent by volume. Which, like any percent, it's the part that you're interested in over the total. So the part we're interested in is the solute over the total, which is the solution. And then you multiply by 100 to make it into a percent. Let's see. We also have ones that are parts per million and parts per billion. Those are kind of like percents, but instead of multiplying by 100, you just multiply by a million or a billion or even a trillion. You can have parts per trillion. That's not on this table, but it's still the information about the part divided by the total. So it's information about the solute over the total solution times 10 to the 6th or 10 to the 9th, depending on if you want ppms or ppbs. Let's see. With this, usually, if you're not told and it's one of these things that you divide two things and multiply by 100 or by 10 to the 6th or 10 to the 9th, then if you're not told otherwise, it should be by mass. Okay, so percent by mass explicitly tells you, but some people might just say percent concentration and they mean percent mass. If they want it by volume, like that second one given there, they would explicitly say that, or we would, because at least in chemistry, normally if we're doing one of these calculations for a percent or a ppm or ppb, we do it by mass. Okay, and then the other common ones that we use are molarity and molality. And so molarity is by far the most common that we would use. And let's see, with that, you can see molarity, they give you the unit. So when you take the moles of solute and divide by liters of solution, you're taking moles over liters. Okay, that's the unit over here, moles over liters. And so when you take moles divided by liters, the unit is a capital M. Okay, whereas for molality, it's moles of solute over kilograms of solvent. So it's moles per kilogram. And that ends up getting a unit that's a lowercase m. So you have to be careful. Capitalization matters in units. So a capital M is moles per liter, whereas a lowercase m is really moles per kilogram. So it's two different things. That's another reason why when you're using moles, you can't abbreviate it as lowercase m, because that is molality. Now these others, for whatever reason, this table doesn't give you units, but a percent by mass, please realize the unit is a percent. Okay, so the number that you come out with should have a percent symbol after it. Okay, whereas for parts per million, the unit actually is ppm, so the number ends up getting that as a unit, and the parts per billion gets a ppb as the unit. Okay. So those things, even though the units in the ratio cancel, or at least most of the time, the mass per volume one, it doesn't, but you just drop them, and you give it the label either percent or ppm or ppb. Now, what you need to be careful with and notice here is most of them are a ratio of solute per solution. Okay, so the top number is how much solute you have, and the bottom number is how much total you have solution. Okay, but the one exception is molality. So be very careful with that. When you're calculating a molality, you need to have only the amount of solvent on the bottom. If you put solution on the bottom, your molality is not going to come out right. Okay, now if it's a really dilute solution, it'll come out pretty close to right, but it's still not right. Okay, so be careful when you're calculating molalities. Okay, let's do some examples. So here I've got consider a solution prepared by adding 2.70 grams of acetic acid to 122.8 grams of water. And I want to know the percent by mass of acetic acid in this solution. Okay, and so if I want the percent mass, then I calculate that by taking the mass of the solute and dividing by the mass of the solution. Okay, and that, you've got to remember, the mass of solution is the mass of the solute plus the mass of the solvent. Okay, so if it helps, you can write it out like that instead of over the mass of the solution. And of course, this is a percent, so in the end, you multiply it by 100 to make it into a percent. So I guess we can write times 100 here and times 100. Some people write that down, some people don't. Just assume you know that you need to multiply by 100. Okay, so if we want to do this, our solute is acetic acid, okay? And so we have 2.7 grams of it, or 2.70. So 2.70 grams of our solute, and we're going to divide that by the mass of the solution. And so our solution is that acetic acid plus water, okay? So we actually need to add the 2.70 grams to the 122.8 grams. And then we multiply that by 100. And so I can sum that together, 122.8 plus 2.70, and oops. So we would really have 2.70 grams over 125.5 grams and multiply by 100. And so 2.70 divided by 125.5 times 100 looks like that gives us 2.15%. for our answer, okay? And you could actually write HC2H3O2 after that, because that's the concentration of that particular solute. You at least have to have a percent symbol there. Whether or not you put the substance next to it depends on if you want to make sure people know what you're talking about or not. Okay, next one. We've got a solution prepared by dissolving 205 milliliters of ethanol in enough water to prepare 235 milliliters of solution. And I want to know what is the percent by volume concentration of ethanol in the solution. Okay, so this time we want the percent volume. Okay, and so that's going to be the volume of the solute over the volume of the solution times 100 to make it into a percent. Okay, and I guess I didn't say this before, but whenever you do a percent by mass or a percent by volume, it actually doesn't matter what unit the mass is in or what unit the volume is in, as long as the top and bottom number are in the same unit. So that percent mass from the previous example, we used grams, but you could use milligrams, kilograms. It doesn't matter as long as the mass on the top and bottom have the same unit. And so same here, the volumes, we can do it milliliters, liters, whatever volume unit we want, as long as the top and bottom are the same, so that unit cancels. And we want to know the percent of ethanol. So ethanol is our solute in this case. And so we put 205 milliliters on top and then 235 milliliters on bottom, because this time we did actually give the solution amount. So we're not going to add those together, because it doesn't say that we combined it with 235 mils of water, okay? And they didn't, because you got to be careful. Volumes aren't necessarily additive. You know, sometimes you mix two things and the total volume's less than the sum of the original ones. Depends on how the particles now mixed pack. Could be different than original. Whereas masses, when you combine masses, you always have the same, you know, the total has to be the sum of what you combined. So you got to be careful. Volumes are not always additive. Okay, they're usually not, actually. Okay, so we have 205. Maybe. I think my calculator died. Yep. Get another calculator. Oh. So 205 divided by 235, and then multiply by 100. And so that gives me a percent of 87.2% by volume of ethanol. Okay. And so that's our answer there. Okay, let's do another one. So this one says, what is the concentration in parts per million of selenium if 0.020 grams is found in 5.0 times 10 to the third kilograms of soil? Okay. So if we want the parts per million, the ppm, that's going to be the mass of the solute over the mass of the solution, and then times a million, so times 10 to the 6th. Okay. And so the solute here that we're talking about is that selenium. So it's 0.020 grams. And our solution is actually the soil. So this is a solid solution in this case. And so soil is made up of all kinds of stuff. And so we're not even concerned about all the other stuff that's in there. We're focused on how much selenium is in that mixture of soil. Okay, so 5.0 times 10 to the third kilograms is on bottom. So now we actually have a little bit of a problem. We can't just divide those and multiply by 10 to the 6th and be done. We need to convert one of those, okay? Now, it doesn't matter which one you convert, but you have to have the right units. And so we could first take, say, 0.020 grams, and convert that, the grams to kilograms. And there's 1,000 grams in a kilogram. And so that's really 0.000020 grams. Okay, so we shift the decimal place 3 times. And so really this number at the top, oh, whoops, that's kilograms. Right, my grams canceled. So the number at the top really is 2.0 times 10 to the negative, what, fifth kilograms. Okay, so if we didn't do that unit conversion, our answer would not come out right. So we have our 2.0 times 10 to the negative fifth. We divide that by 5.0 times 10 to the third. And then we're going to multiply by 10 to the sixth. And that gives us 0.004 ppm. Okay, so it probably would have been even better if we would have converted it to ppb, because ppb then would have multiplied by another 10 to the third and given us 4 ppb. So that would have been a little more reasonable, but that's okay. Okay, next up, we have a solution that contains 117 grams of KOH dissolved in enough water to make a 2-liter solution. What's the molarity of potassium hydroxide in the solution? Okay, so we want a molarity, and molarity is moles of solute. So N is what we use for a symbol for moles. So moles of solute over the volume of our solution. Of course, that needs to be in liters. And so we would take, well, the 117 grams, we need moles. So KOH is our solute. So I'm going to first take my 117 grams of KOH, and I'm going to convert those grams KOH to moles of KOH. And so I need to add up potassium, so 39.10 plus oxygen 16.00 plus hydrogen 1.01. That gives me a molar mass of 56.11 grams per mole. And so then that's going to give me, let's see, 117 divided by 56.11. So I actually have 2.085 moles of KOH. So I'm keeping an extra sig fig because we're not done with the calculation. So 2.085 is my moles, and that is got to be put over the liters of solution, which was given 2.00 liters of solution. So I take the 2.085 and divide by 2.00, and that gives me a molarity of 1.04 molar of KOH. Okay, so I wrote the unit as a capital M. You can also write it as 1.04 moles per liter if you want. That's okay as well. But what is not okay, what I see a lot of people do, is saying capital M equals 1.04. That's telling me the letter M equals 1.04. Well, that's meaningless. You have to have a unit next to a number, so don't ever do that. Okay, so the unit goes behind the number. It's not unit equals number. Okay, so just don't do that. No one likes that. Okay, let's do one more. So now we have a solution. It contains 56.7 grams of KOH dissolved in enough water to make a 245.8 gram solution. And I want to know what's the molality of the solution. So molality is equal to the moles of solute. Okay, so again, N is my symbol for, or the variable for moles, okay, over the mass of the solvent. And specifically that mass is in kilograms, okay? So let's see, do we have moles of solute? Well, not exactly. We have grams. So we have 56.7 grams of KOH. Okay, and so we can convert those grams of KOH to moles of KOH, and it's 56.11 grams per 1 mole. And then, let's see, that gives us 56.7 divided by 56.11 gives us 1.011 moles. So again, I'm keeping an extra sig fig at the moment because we're not done with the calculation. So I have the moles of solute. So I have my top number. Now on the bottom, I'm going to need kilograms of solvent. Now we were given grams of solution. So that's not solvent. You have to be very, 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 very careful. So you have solution and you have solute, okay? And remember, solute plus solvent equals solution. So I can take that solution, the total mass of 245.8 grams, and I can subtract off the solvent, the 56.7 grams, okay? So this is my solution. And this is my solute. And that's going to give me, let's see, 245.8 minus 56.7 gives me 189.1 grams. And that is the solvent. Okay. And so now I'm going to convert those units from grams to kilograms because I need it in kilograms. And there's 1,000 grams in a kilogram. So that gives me 0.1891 kilograms. Okay. And so I can plug my numbers in now because I have the moles of solute and I have the kilograms of solvent. So it's 1.011 moles over 0.1891 kilograms. So 1.011 divided by 0.1891 gives me 5.35 molal. Okay, so a little m. And that's KOH. Oh, that wasn't supposed to happen. Let's see. Get back to slide. There we go. So we have that. You can also write it as 5.35 moles per kilogram. Okay. Please do not write M equals 5.35. That is meaningless. This is not the proper way to write it. Okay. So hopefully that helps you get started doing some concentration calculations. Most of the time we deal with molarity, so remember it's moles per liter, okay, moles of solute per liter of solution. That's the most common that we use in chemistry, but realize there are other units for concentration, and so if you need to know what they're made up of, you can always use a resource. So like that table that I've got on these slides, you can use that to look back up what you should be calculating a ratio of.